Alright, area of study 2 in unit 4. So light and matter. So it's called how light and matter are similar. So what we can do is here have a look at some experiments and things to give us the idea of the connection between the two things. So first of all, the photoelectric effect is what we're looking at in this particular lesson. That's the main thing. So a little bit of background here, Bohr theory. So we had a little bit on Bohr. So Bohr came up with the idea about the atom, that there's the nucleus in the centre, and then there's electrons around the outside, and they're in particular energy levels. All right, and so he said that they could, if an electron was here, it could move up to that level there if it got the right amount of energy, and then wouldn't really want to be there, so it'd drop down, and then some light would be given off. And so we looked at that a little bit in year 11 in unit 1. All right, so then that was Bohr's idea, very famous physicist. And then in 1925, two guys, Frank and Hertz, they designed an experiment to test those predictions, and their results supported the theory. And they got the Nobel Prize. All right, so that then leads on to the idea of quanta. And if you like, it comes from the word quantity. And quanta, quanta, the idea of quanta comes back to this Bohr stuff. You know, it can go up there or it can go up there, and same if it drops down, it can drop down there, or it could drop all the way down. You know, or if it drops to here, then it could drop again. So there's certain amounts of energy that are given off. And so quanta, if you like, is that the packets of energy that are given off. Okay, and they're in discrete amounts. So they're not any random amount. They're discrete, certain predicted amounts. All right, and so the quanta in this case, when it's given off here, these quanta we call photons. So photons, quanta, given off when electrons drop down levels. All right, and from that Bohr used Max Planck's equation for the energy of a photon, and Planck had come up with the idea. So this is the space in your notes. The energy of the photon is related to Planck's constant and the frequency of the light. All right, so that's Planck's equation. Planck's constant is h. We'll get to that in a minute. And so if we're using the wave equation, V equals lambda f, and of course if we're talking about light, then V is equal to c, so we're looking at c equals lambda f. And we rearrange that, and we get then that f is equal to c on lambda if we divide both sides by that, and then we put this in here instead of f, and so we get that the energy of a photon, and this is the other gap in your notes, is equal to h. It's an ugly looking h, hc on lambda, where h is Planck's constant, c is the speed of light. So Planck's constant, there's two versions of it as it shows in your notes, whether you're looking at energy being in joules or whether it's in electron volts. And so one of them is 6.6 by 10 to the minus 34. and that's joule seconds. And so that's if your energy you want in joule or it's given in joule, that's the Planck's constant version. The other version is 4.1 by 10 to the minus 15 electron volt seconds. Alright, so if you want the energy in, or you are given it in electron volts, then that's the one you use. Alright, so as it says in your notes there, an electron volt is the amount of energy an electron gains moving through a potential of 1 volt. So it's only a very small part of a joule. And so if we put 1 electron volt, as this in your notes is also is 1.6 by 10 to the minus 19 joule, which you may or may not recognise that number as the charge on an electron. Alright, so it is an electron being accelerated through 1 volt, so it makes sense that it has the charge on an electron wrapped in there somewhere. Alright, so let's have a look at an example, or a couple of examples. Here we go, calculate the energy in joule of a photon of ultraviolet light with frequency 7.4 by 10 to the 14. So our energy of our photon is equal to HF. Now it's asked for in joule, so we're going to use the joule one, so that's the 6.6 by 10 to the minus 34 times the frequency, which is 7.4 by 10 to the 14. So stick that in your calculator and you get 4.9 by 10 to the minus 19 joule. Alright, example 2. What is the energy in electron volt in of a photon of red light of wavelength 640 nanometers? Alright, so first of all, this time we're given the wavelength, so we'll use the version which has the wavelength in it, the photon hc on lambda. And it's electron volt, so we use the electron volt version of, there it is, 4.1 by 10 to the minus 15. Times c, which is the speed of light, 3 by 10 to the 8 metres per second, over lambda, the wavelength, 640 nanometers, nano, so nano is 10 to the minus 9. And we whack all of that in our calculator and we get 1.92 electron volts. Alright, so there's an example, or a couple of examples. Righto, the next bit, this is the main bit, photoelectric effect. Alright, so the idea of photoelectric came was if we had electron here and it dropped down a level and then we got some light given off, people thought, alright, what about the opposite then? What about if we have got, and we shine some light in there, can we get some electrons shooting out? So that was the whole idea with it. And so people thought, can that happen? Now the short answer to that is yes. But, right, it's not as simple as it seems. Because there's quanta involved. And so there's certain energy differences between these energy levels in the atom, so you've got to be able to give the right amount of energy, otherwise the photon doesn't. And also, what was found out, that the photon's got to give up all. So the photon must give all energy, right? Not part of it, and the energy needs to fit the energy levels. All right. So how did they find this? All right. So they found it out by setting up an experiment, something like this. All right. So here's an idea. So here we've got what we call a photocathode. So when light comes in here, here's the light comes in here, hits there, the cathode, we get some electrons maybe can come off. Can they or can't they? That's the idea. All right, and that's in a sealed vacuum tube so that there's no air particles in there for the electrons to bump into. And so we've got a voltage here, so we can make this positive if we want, but we can also variable, so we can make it negative if we want as well. So if we've got electrons coming off, they may jump across. So if you've got positive there, then yep, they'll get attracted and over there. And then there'll be some sort of, and they'll go around, of course they'll go around through there, back to the cathode, because now the cathode needs more, it's got less electrons than it wants, so it'll go around there. All right, so people thought, oh yeah, that's all right, that looks pretty exciting. So they played around with these things. All right, so they played around with voltages and all of that sort of thing, and what they found is that sometimes, even if you made this negative, you were still getting some electrons coming across. And so they made that more and more negative until they stopped it. All right, because originally, as it says in your notes there under the diagram, originally when they turned this off altogether, there was still electrons coming across. All right, so then they go, all right, well, we'll make it negative. And so what it got to is it got to a certain point where they could stop all those electrons. All right. So all in your notes, all those words is just kind of saying what I'm saying. So when we got this negative voltage there, and we turned that up and we making this negative to try and stop our electrons, what I found was that there was a certain voltage, and we'll call it V0. That's the voltage where we can stop all the electrons. Now, of course, when these electrons leave and they head out that way, they've got kinetic energy. Okay? So if we want to stop all the electrons, they'd be the maximum kinetic energy, the most energetic electrons that once they're all stopped. All right? And so you might think, oh, how is that? Well, remember there's shells. So these ones out here in the outer shell, doesn't take much energy to remove them, so the rest is kinetic. These ones here, it takes a bit more, so they'll come out, but with less kinetic energy. And if the electrons way in here, they'll come out. Oops. They'll come out with less kinetic energy again. Okay, so what can we determine from that, and this is about halfway down page 3 here, is that the kinetic energy, max, is equal to the work done to stop the most energetic electrons. So if we think back to last year, and so with that voltage that stops it we call V naught, then our kinetic energy max is QV, but in this case QV naught, and so V naught is our stopping voltage. Alright, and there's some good videos here, so watch the videos to get a different view, because this is a kind of a little bit, can be a little bit freaky, this stuff. Alright, so I've got that space there twice, I don't know why I've got that, but anyway. So the units are electron volt or joule, depending on what you use for your charge, whether you use charge in Coulomb or charge as in charge on electron. Alright, so what they also found when they were shining this light on here was that increasing, so there's some light, so for a particular photocathode, particular material, it didn't matter what light you shone on there, how strong and how bright it was, you wouldn't get anything out, which seemed a bit strange. But those that did, when you shone light, what happened over here was with the current, so for the brighter light, we had a higher current. So what that suggests then, so it was a higher current, not a higher stopping voltage. Alright, so if it's a higher current, remember current is charge over time. But our stopping voltage was the same. So for brighter light, so the stopping voltage determines what the kinetic energy of the electron is. And so it seemed that the brighter light didn't change the kinetic energy of the electron, but you had a higher current, which involves Q, which involves the electrons. So in your notes there, in point number 1, there, higher intensity of light means more photons. Alright, so each photon's the same energy, but we got more photons, not more energy per photon, right? And if you look at this graph, which is in your note, this graph kind of indicates. So here we've got green light, and our stopping voltage is the same, depending, regardless. But for green light, for low green light, we get up to this point, and then we get that current. For medium light, we get a higher current, and for bright green light, we get a higher current again. Now, you'll notice that these stop out and get flat. So the reason for that is, remember, the stuff has electrons. And once you've got these electrons and all the others above out, well, there's no more electrons to get, so you can't get any more current. And so that's what's happening in this section here, where it flattens off. All the electrons are being removed, and so you can't get any more electrons, you can't get any more current, because remember, current is charge over time, and it's the electrons that carry the charge. Alright, the second thing in your notes there was number 2, that it must give up all energy. Alright, you can't share it out. must give it all. And that's what they found, because if they shone a light on there that was a low frequency, so like remember energy is HF, so a low frequency, then they would find that they wouldn't get any electrons off, and no matter how bright that light was. So what we have, here's another graph. It's not really related. Well, it is related to that actually, so I better put it. That's this graph here. So violet light has a very high frequency. So if E equals HF, remember, high frequency, high amount of energy. So if it's got a high amount of energy, it's going to take quite a bit of voltage to stop those electrons. Green light, low frequency, lower energy, not as much voltage to stop those electrons. Alright, so that's this bit, the photon giving up all its energy. So the high frequency, high energy violet light photons give up all their energy, and so those electrons are moving more quickly. Alright, and so again, each of those is the saturation point. So on this, the intensities of the light are different, so we can't really compare this section, but this section down here is what we are talking about here, give up all the energy. Alright, so this stuff's a bit freaky. Alright, so the next bit was if we plot a graph with the maximum kinetic energy of the photoelectrons, in electron volts this is, against frequency and different cathode materials. So just on here is just a bit of an idea. Visible light's down this way, ultraviolet's up that way. So you can see potassium and magnesium, two different ones, and you see that they actually get a different line. Alright, so from this you need a higher frequency of light for magnesium to start removing electrons than you do for potassium. Now that's when they started removing, because down here underneath the graph down here, that's negative energy, so that's theoretical. But if we do, because this is a straight line, if we trace it back, each of those strikes the vertical energy axis at different place. And what that indicates, it's called the work function, what that indicates is the amount of energy needed to remove electrons. Alright, so we don't get electrons removed until here. So if we trace that back, and it's going like, okay, so what we need is 6 electron volts worth of energy to remove an electron from magnesium. Now you also notice it's a straight line, and the gradient of that straight line is Planck's constant. Alright, so when they did that, it was very interesting. So down here, in this area down here, if say we're looking at potassium, and we're looking at a frequency of 3 by 10 to the 14, no matter how bright that light is, we're not going to get any electrons off it. Alright, so in your notes there's a few dot points here. First of all, threshold frequency. So the threshold frequency is these points here. Alright, threshold frequencies there and there. So below that frequency, you can't get electrons emitted. And the threshold frequency is different for different materials. So there's the first two dot points. The gradient of the graph is the same for all metals, and I already said it's Planck's constant. And then the next dot point, and let's go over here, is this next dot point's more important one, is that the energy, kinetic energy of that photon will be the HF, the energy of the photon, minus the work function. So minus how much it's going to take to get that electron out of the atom. Alright, so work function. So energy to remove electron. Oh yuck, that removes a bit ugly, isn't it? Anyway, not to worry. Now, just as an aside, your textbook for work function uses this symbol phi. So if you're looking at your textbook and you get confused what's going on, that's what they're doing. All right. The last two dot points are kind of already talked about. All right. So then there's a summary of the results. So the first one there. So the stronger the beam of light, so more intense beam, more intense light led to greater photoelectric effect, more electrons. So, all right. Each material has its own threshold. All right, we call that F naught. So the maximum kinetic energy of electrons is independent of intensity. And the last dot point there, and this was weird because they put some pretty low light in there, the emission of electrons is immediate. Okay, so in your notes it says less than 10 to the minus 9 seconds. So it didn't matter how bright or dull, how weak the light source was, because remember we're now talking about light sources as photons. All it takes is one photon to be hit, one photon of the right energy to hit an electron, and bang, out that electron goes. Alright, so let's have a look at an example. Okay, here's the example. Sample of potassium is used as a cathode of a photocell with which the photoelectric effect is studied. When green light of particular intensity is shone, the following current volts graph is obtained. Also, the threshold frequency is found in the yellow region of the visible spectrum. Alright, so we're shining, the threshold is in yellow. So what do we need to know? We need to know Roy G. Biv. Alright, and we're told that it's in the yellow region is the threshold. So things down this way are higher frequency, and things down this way are lower frequency. So that, of course, has to do with the energy as well. So in the first one said what current would be expected if the red light was shone onto the cathode. Okay, and so seeing as yellow's the threshold and red light down here is a lower frequency, lower energy, so there's not going to be enough energy, so 0 volts. Oh, 0 amps, talking about the current. Alright. Part B says draw a graph would result if the intensity of the incident green light was doubled. So remember, if the green light is doubled, I'm going to rub those out there. If the green light is doubled, what that means is we're getting more photons. So we're getting more photons, so this saturation current will be bigger, and seeing as it's doubled, you expect it maybe to be doubled. So I'm now thinking that our green light will go like that, so that's double intensity. So it would go like that. Alright, the next one says draw the IV graph that would be result if violet light of a low intensity. Alright, so violet, and I'll rub that bit out, that Roy G. Biv stuff out, didn't I? Let's put that there. And remember, this is the threshold. So violet down here, there it is, violet down there. So violet's quite a fair way from yellow, so it's going to have a fair bit of more energy. So if it's got a fair bit of more energy, it's low intensity, so it's going to be like there. But if it's got a fair bit more energy, it's going to take more volts to stop it. Alright, so if it takes more volts to stop it, it's probably going to end up way down here somewhere for its threshold. So we need a larger stopping voltage there. Alright, when a UV light is incident on the cathode, stopping voltage is found to be 2.25 volts. Determine the maximum kinetic energy of the photoelectrons in joules and in electron volts. Well, let's do the electron volts one first, because that's the easy one. Because these are photoelectrons, you've got one electron times 2.25 volts. So in EV, we have the energy is one electron times 2.25 volts, which is 2.25 electron volt. And in joule, what we need to do is we just need to change that to joules. So the energy then would be 2.25 in electron volts times the conversion factor, which is 1.6 by 10 to the minus 19. And then when you multiply that in your calculator, you get 3.6 by 10 to the minus 19, and that is joule. Alright. Alright, the last little bit. So there's a bunch of conflicts between classical theory and the results of these. Alright, so this is in your notes. So the first thing here is the immediate ejection of electrons, even for very weak light. Okay, so the classical theory would have said light's a wave, so the wave delivers energy continuously. So the electron would sit there absorbing the energy, and then when it got enough, boom, it'd jump out. Alright, so according to classical theory, it'd take time for that to happen, and so the electron would be a while till it got enough energy, so it'd take some time, rather than being bang off all at once. Almost immediately, I should say. The second one was the electromagnetic radiation. The energy of a wave is proportional to its intensity. Alright, so classical theory says higher intensity means that it has more energy. So you should be able to crank it up and then you get more energy. And that was not found. It was found that there's a threshold frequency. So it didn't matter how, if the light was below the threshold frequency, it didn't matter how bright it was, you wouldn't get anything off. And again, that was a bit weird, according to classical theory. And also the other thing was that more intense light should increase the energy of the ejected electrons. So you got more intense light, more energy, so the electrons should come off faster. But it was found that it didn't, not on intensity, but on frequency. All right, so these are conflicts at the time between classical theory and what the results were showing. All right, so there's one example, and then some questions, and then there's quite a few exam type questions at the end of this. And then to answer that question and figure out how we can get our head around the conflicts between these results and the classical theory, you'll have to wait till the next lesson. All right, the example. Okay, so we've got a 100-watt light globe produces yellow-green light of wavelength 500 nanometers. Determine the number of photons released from the globe every minute. All right. So, total energy. So remember, power is energy over time. So the energy then will be the power times the time. So the power is 100, and it's talking about every minute here. So every minute is 60 seconds. And so that is 6,000 joule of energy. All right, so the energy of our photon, and I'm doing this slightly different than I did it in the notes there, but that doesn't matter. It's the same, but different. So the energy of a photon is HF, and H there is 6.63 by 10 to the minus 34, and because we've got to work in joules, so I've got to use the joule one, times, well, frequency. Remember, I've actually used I should have, before I got to that, I should have said that, C equals lambda F, or V equals lambda F, the wave equation. C, so the frequency is C over lambda. So that is, where am I? So I should going to use this here instead of F. Let's put that in there, right? So 3 by 10 to the 8 over 500 nanometers, 500 by 10 to the minus 9. All right, so we've got 3.978 by 10 to the minus 19 joule for a photon. Now we've got 6,000 joules, so there's got to be more than one photon because each one only does that much. So the number of our photons then has got to be equal to 6,000 joule divided by the 3.978 by 10 to the minus 19 joule. And when you do that, you get 1.5 by 10 to the 22 photons, which is a lot of photons emitted each minute. All right, So that's it. That's the end of the first lesson. So there's some textbook questions. There's also a whole bunch of past exam questions and their answers that are there in your notes. So, of course, as always, if there's anything you need clarifying, and this is again one of those things that challenges your thinking, make sure you ask. There's some good videos there on the website as well that you can watch that explain a bit more about the photoelectric effect.